All right, welcome back. Going to look at the Biot-Savart Law again, but the point here in this video is to show you that that law can be written in a more mathematically precise way. You know, the way we've given it to you, or I've given it to you, is you've got a formula, and then you got to figure out a direction. It'd be nice if we had a way to do that where when we calculated it, it not only gave us the magnitude of the field at a point, but it also gave us the direction so that we didn't have to necessarily figure it out, because in some cases, you know, you may be able to do the right hand rule and know, well, it's got to point in a certain direction, but it's kind of hard to define that direction because it may not be purely in the X, Y, or Z direction. So let's look at this, looking at the Biot-Savart vector product form. See, that law, the Biot-Savart law, can be written a whole lot more compactly if we use this thing called the vector product, which a lot of times you'll hear me call it the cross product. Both of those, that's synonymous, vector product and cross product. Now, I think most of you should have encountered cross products by now, but let's just kind of go over what a cross product is and make sure you understand that, because if you can get those basics down, then it's going to be an easy leap for you to see how the Biot-Savart law can be written using a vector product. So let's talk about vector products. Let's put up a three-dimensional coordinate system. You can see I've got my x-axis going this way, my y-axis going this way, so this xy plane is what we're used to working in. But now I've added the z-axis, okay, perpendicular to both the x and the y. So, you know, like I said, when we start talking about magnetic fields, it's kind of hard to get away, you know, from that three-dimensional perspective. All right, let's consider a couple of vectors, and I'm setting these up so it's not hard to see because I want to get the point across. All right, so let's say we have a vector A that points right along the x-axis. It's pointing the positive x direction. And we have a vector B that's right on the y-axis and pointing in the positive y direction. Now, let me start out with just the basic definition. The cross product of two vectors, or the vector product of two vectors, which is denoted by this language. Say we wanted to cross A and B. A cross B is just equal to the magnitude of A times the magnitude of B times the sine of theta. Okay? And so this is the mathematical definition of the cross product. Now the thing is, okay, vector products, they produce another vector. You got two types of ways a lot that you multiply vectors a lot. You've got what's called the cross product, and you've got what's called the dot product, or the vector product and the scalar product, okay? Scalar products, like when we were calculating work, F dot dr, they produce a scalar quantity, right? Well, the cross product produces another vector, okay? And the magnitude of that vector is given by this quantity right here. But the question is, well, if it's a vector, it's got to have a direction. So how do we figure out the direction? Well, here's the thing. The direction is always perpendicular to the plane that contains those two vectors. So what plane contains the x and y vectors? Think about that for a second. What's the plane that contains both those vectors? Well, hopefully you said, oh, it's this plane right here. It is actually the xy plane in this situation, right? And so what that means is that the cross product of these two vectors is going to have to be another vector that is perpendicular to the xy plane in this situation. That's what this is saying. But now there's two ways that it could be perpendicular. It could be pointing in the positive z direction, or it could be pointing in the negative z direction. Both of those directions will be perpendicular to the xy plane. And the question is, well, how do we figure out if it's pointing in the positive z or the negative z? Well, you do it by using the right-hand rule, okay? So what you do is you basically are going to rotate the first vector, okay, A, into the second vector, B, okay? And we're going to use our hand, again, to see this. And when we rotate our fingers from A to B, our thumb is going to point in the direction of the cross product. So do that right now, okay? Here's what I want you to do. I want you to line up the fingers with the right hand, of your right hand, okay, with vector A. And I know this is kind of hard to do, but, you know, try to get them in line with that, okay? And in this case, your palm is going to face up. Because if you put your palm down, then you wouldn't be able to rotate your fingers backwards in the B, would you? No, you wouldn't be able to do that. So you want to have your palm up, pointing in the direction of vector A, okay? And then what I want you to do is rotate your fingers, curl your fingers up so that you make a fist by rotating them towards vector B, okay? Now, if you do that, which way is your thumb pointing? Is it pointing in the positive Z direction or the negative Z direction, okay? Well, hopefully, if you've done it right, your thumb is going to point in the positive Z direction. And so what that means is that this cross product, okay, it has to be a vector that's perpendicular to the XY plane, and it's pointing in the positive Z direction. So if we were to draw it on this coordinate system, it would look something like this. Here it is. It's a vector pointing along the positive Z axis, and it's got a magnitude given by, take the magnitude of A times the magnitude of B, and then multiply them by the sine of the angle that is between them, okay? That's what this is saying, that theta is the angle from A to B, okay? Now, I hope you notice something. Order matters with cross products. A cross B produced this vector that points out, right? If instead we had reversed B and A, well, we'd have the same magnitude, but in that case, we would be curling B into A, so we'd have to line our fingers up with B and rotate them over towards A, curl into a fist, and then you would see that your thumb is pointing in the negative Z direction. So if you take B cross A, it's the opposite, in the opposite direction of A cross B. And so that means you've always got to get your directions right, okay? Because if you accidentally curl your fingers from one vector to the other in the wrong direction, you're going to get a wrong overall direction for your vector product. So that's how the vector product works. Now, here's the thing. I told you that it was a way to figure out direction for, those awkward things. This works with a right-hand rule because the answer turns out to be in one of the directions that's principal. It's in the Z direction, or so we could do that for vectors that are in the XY plane, vectors that are in the XZ plane, vectors that are in the YZ plane, because those are always going to have a perpendicular that's along one of the other axis directions. But what happens when one vector is coming out at an angle and it's over the XZ plane and the other one's going down? You can still curl your fingers, but you don't have any sense of what direction that is. Well, how can we get a vector then that would actually contain the direction? Well, there's another way to do A cross B, all right? Turns out that if you wanted to take A cross B, you can do it by taking the determinant of this matrix. Notice it consists of 3 rows. The first row contains the unit vectors. The second row contains the components of A. Always put the components of the vector your fingers would start at on the right-hand rule. That goes in the middle, the first, under the unit vectors. And then your second vector's components B would be BX, BY, and BZ, okay? And, this is mathy right now, and hopefully you've done this before, but when you take the determinant, you take, what it turns out to be is it's going to be the smaller determinants. You mark out like the first column, the first row, I hat will be multiplied by AY, BZ minus AZ, BY. But this is getting mathy, but here's how you could actually calculate the components of the vector, and the direction's always contained there, right? I mean, if we've got it in unit vector notation, we can always work from that unit vector notation to figure out the magnitude of that vector and its direction if we wanted to. We could get the angles and spherical coordinates, okay? We're not going to be doing this in the class. I just want you to see that when I told you writing it in the cross product form can help us find directions for awkward vectors that don't line up nice and neat for our right-hand rule. This is how you can do it. There's actually another way that I do in statics. We do cross products a lot in statics, and I have another method to show you that's a little bit easier to remember, I think, than trying to remember to take all these little determinants of subsections of this matrix, okay? But that's the cross product. The key of the cross product is it always produces a vector. It does. It's a vector product. It produces another vector, and that vector is going to be perpendicular to the plane in which those other 2 vectors are contained, okay? Now, let's think about this for the magnetic field strength using the Biot-Savart Law. Let's go back to a picture that I pulled out of your book, Physics for Scientists and Engineers by Randall Knight, 4th edition. Great book. Here's the picture. We've got a positive charge, okay? and it's moving in the direction there. We want to know the magnetic field that's at position R from where this is at. And of course, we know that the magnetic field's got to be perpendicular, and it's going to be pointing this direction based on the right-hand rule. Okay, pointing your fingers along V, curling them up to R, and your thumb is pointing out, okay, the direction that this arrow is showing. Okay, now the Biot-Savart law says that the magnitude of that point charge's magnetic field at this position is given by this equation, right? And the direction is given by the right-handed rule. Now, when we start seeing things like, oh, I've got the sine of an angle up here, I've got a vector up here, you know, stuff like that, the directions found by the right-handed rule, that makes us think, oh, maybe we could write this in terms of a cross product. And we can. If we wanted to write this in terms of a cross product, we would write it this way. The magnetic field of a point charge is just equal to mu naught over 4 pi times Q with V crossed into R hat. Now, whoops, my R hat got moved. This R hat was supposed to be down here on this R, so visualize it down here, okay? We would cross V into R hat, okay? And that's going to give us R squared. That's really bothering me that R is there. Hang on, I want to see if I can fix this real fast. Let's pull it down here where it's supposed to be because it's going to annoy me. Let me pull it down here. Okay, hit go again. Now, let's see if this comes up. So there it is again. We could write it that way. Now, good. My unit vector is on my R. Sorry for that. That's a little bit of a waste of time there. But so what it says, we can take find that magnetic field of that point charge. These are all constants, but we can take V and cross it into R hat. Now, what's R hat? R hat is just a unit vector that points along the position vector of the point that we're interested in. It's a unit vector, though. What's its length? Well, it's the length of all unit vectors. It's 1, okay? Let me show you how this quantity, this V cross R here, R hat, gives us this, okay? Remember that first way of calculating the cross product, okay? If I have V cross R, well, that's just going to equal the magnitude of V times the magnitude of R hat. I keep saying R, but it's R hat, the unit vector, times the sine of theta. So that's how we would calculate the magnitude, right? Well, remember, R hat is a unit vector. Its length is 1. So it's going to disappear, and what I'm left with is V sine of theta. So this V cross R hat portion right here gives me this back up here, the V sine of theta. And so this is a way that we can actually write the Biot-Savart law in terms of a cross product. And again, the cross product will pull the direction out. Now, that doesn't mean we're not going to keep using the right-hand rule. There's a lot of problems that you'll work where that's the basic way to do it, and it's easy. But for those weird angled stuff, you know, when V and R are at weird angles, not in any of the XY plane, YZ plane, you know, ZX plane, then the Biot-Savart law in this cross product form, man, that's really helpful, okay, and getting the direction. All right, so let's just take a look at a problem, that we can do, kind of thinking about how the cross product works, all right? So we have an electron here, and it's moving with a velocity v to the right. And we want to know what's the direction of this electron's magnetic field down here at the dot. Okay, well, how would we do this? Well, first of all, we know this. V and R hat are in the plane of the screen that you're viewing right now, right? And so the magnetic field at that point, it's going to have to be perpendicular to your screen. And so it can either point out of the screen or it can point into the screen. Now, to figure out which one it is, we got to use the right-hand rule, right? So what I want you to do is I want you to point your fingers in the direction of V. For me, here, I guess maybe I can come on this side and reverse it. My fingers are pointing straight out, right? Okay. Now, when I curl my fingers, right, remember, point your fingers in the direction of P. Now, your palm will have to point down this time because you want to be able to curl your fingers into a fist in the direction of R hat. That's what that means, right? So you point your fingers out, palm down. Now, curl them into R hat. Which direction will your thumb point? Well, if you're holding your thumb out straight and you've positioned your fingers correctly at the start, then what you're finding is that it's pointing into the screen. Okay, so you curled your fingers into a fist, you held your thumb straight out, and now it should be pointing into your screen. Okay, so there's the direction that you would curl your fingers. But now here's the thing we got to be careful of, because we said, oh, the magnetic field's pointing into the screen. But there's a problem. When your finger's pointing into the screen and you've done this right-hand rule, you're finding the direction of the magnetic field of a positive charge. Okay, that right-hand rule is set up for positive charges. But we know that our charge is an electron and it's negative. And the thing is, the magnetic field of an electron will point directly opposite the magnetic field, say, of a proton. And so your right-hand rule has said the directions into the screen, but you've got to look and say, oh, wait, it's a magnetic charge, so, or a negative charge. And so it's got to be pointing opposite that. You'll have to know to turn it around. But again, that's how you use the right-hand rule. You use it as if though you've got a positive charge. Then you look at it and say, well, do I really have a positive charge? If you do, then it's pointing in the direction your thumb's pointing. If you don't, if it's a negative charge, then it will be pointing opposite the direction of your thumb. And so that's something to always be aware of. Negative charges and positive charges produce fields in opposite directions. Okay, so I wanted to do this to show you how to use the right-hand rule, but I also wanted to introduce the negative charge to show you things get switched around. Okay, we're going to stop there. We just got the Biot-Savart Law into cross-product form. Now what I want to do is move into, well, how do we actually handle currents, okay? Because everything we've done so far has been for single charges, but current consists of a multitude of charges. What do we do in that case? And that's what we'll get into in the next video.